Welcome to part 2 of NatureServe's data use training, the data we provide. In this module of the training, you will gain an understanding of the scope of biodiversity data that NatureServe develops in collaboration with our network programs across the US and Canada. And you'll learn ways that you can access this information. The data developed by NatureServe focuses on answering 3 primary questions that are critical to accurately assessing the status of biodiversity. What is it? Where is it? And how is it doing? So looking at the first question, what is it? Before any conservation action can be taken, we first need to know what we're trying to protect. NatureServe maintains taxonomy on North American plants, vertebrates, and invertebrates. We also partner in the development of a standard classification for North American ecosystems. Altogether, NatureServe tracks over 100,000 species and ecosystems using standard classifications, as shown here in the graph. Use of standard classifications and taxonomy are critical to ensuring that our data are consistent and comparable. Geographically, we focus on species and ecosystems in the US and Canada. Taxonomically, we focus on tracking not just vertebrates, but the invertebrates and plants that make up the majority of life on planet Earth. Our ecosystem classification encompasses both broad groups like forests and grasslands, down to very specific vegetation communities, such as the redwood western sword fern forest. Looking across all levels of the vegetation hierarchy, we help describe and track approximately 1,000 different ecosystem types. This slide gives you a visual of the many species groups we track. NatureServe maintains comprehensive taxonomic information, status information, and habitat information for many groups, including all the groups shown at the top of this slide. That includes vascular plants like trees and orchids, vertebrates like birds, amphibians, mammals, and fish, the freshwater invertebrate groups shown here on the top row, including freshwater snails, freshwater mussels, crayfish, and shrimp. The second row shows the insect groups that we comprehensively track, including bees, butterflies, skippers, moths, dragonflies, and the other groups shown in purple. NatureServe also tracks data for North American ecosystems under the International Vegetation Classification. The bottom part of this slide indicates other groups that we are tracking at least partially, and we're continually adding additional groups that are priority for conservation. Although NatureServe tracks basic information for all of the groups described above, our network programs only map the spatial locations of the most imperiled species in these groups, which we'll talk about next. So this brings us to the second question, where is it? For the species and ecosystems we track, we maintain robust spatial data products. Our biodiversity location data provides essential information on the location of species and ecosystems. The graph shown here gives you an idea of the breadth of spatial data NatureServe and its network programs manage, including over 1 million documented occurrences of at-risk species and ecosystems. We document whether a species or ecosystem occurs within states, territories, or provinces. And for at-risk species and ecosystems, we map the precise locations based on field inventories. And to help fill the gaps for areas where we have not yet surveyed, we have developed species habitat models that identify where on the landscape species are more likely to occur. Lastly, we have vegetation maps wall to wall to fill in additional information for the entire landscape. The combination of species and ecosystem data products are very complementary. The information for individual species provides a fine filter for conservation, making sure that none of the unique elements of life fall through the cracks. And information for ecosystems provides a coarse filter for conservation, ensuring that healthy examples of all major habitat types persist into the future and support the many species that compose of these ecosystems. This slide indicates 2 different groupings of location data that we develop and manage. On the left, we have the observation data and element occurrence data that represent the documented distribution of a species. These are places where species have been observed and verified in the field. On the right, species habitat models and range maps are different ways to map the potential distribution for places where species are likely to occur but may not have been directly observed. So first, looking at observations. Observations represent where a species or ecosystem has been observed. They're important for habitat modeling, for tracking wide-ranging and widely distributed species, but they do not always indicate the critical locations for conservation action. Currently, NatureServe does not aggregate observations across our entire network, but we are using observations to inform the development of other data products. The next version of our data management system will support the aggregation and provision of observation data. And we've already developed an observation data collection tool that is in use that promotes the standardized collection of observation data. Element occurrences are observations that have been taxonomically verified by trained biologists and developed using accurate measurements of location and standard mapping rules. All of these things ensure that locations are comparable across the species range. Element occurrences are evaluated to include information about the condition or status of each location. Element occurrences are a unique concept developed by NatureServe that target areas that are, if conserved, contribute to the persistence of at-risk species. The characteristics of the element occurrence contribute to its quality and make it invaluable for informing conservation priorities and resource management decisions. We'll provide more information about the element occurrence in the next section of this module. The first type of predictive model we'll talk about here are species habitat models. Species habitat models represent places where a species is likely to occur using methods that identify conditions similar to those where a species has been observed. Our models identify habitats where there is a high, medium, and low probability for the species to occur. Although some models perform better than others, we provide metadata indicating the confidence of each model that includes detailed information why each model performed the way it has. Models are available for many, but not all imperiled species, but our modeling team is continually creating and improving our library of habitat models. We will go into a little more detail about species habitat models in part 2B of this training. Our other predictive data product is our vegetation maps. Vegetation maps help us understand what is happening across the entire landscape. These maps are representing places where an ecosystem is likely to occur based on methods that identify environmental conditions or spectral signatures consistent with an area an ecosystem has been observed. This allows us to comprehensively show the distribution of mid to high levels of the National Vegetation Classification hierarchy for the US and temperate Canada. And last but not least, range maps are an important data product. Range maps represent the general geography in which a species or ecosystem may occur, but they can include attributes that indicate the historical as well as the current presence of a species or ecosystem and indicate seasonal use of habitats by species. They can be useful also in guiding the development of species habitat models and in conducting other types of analyses that require consideration of a species' full range. Currently, NatureServe is working with our network programs across the US and Canada to develop a methodology for developing range maps for all the species that we track. And we will begin to make those available in addition to the current range maps we have for many at-risk species and ecosystems. After we have answered the questions, what is it and where is it? We then need to answer the question of how are species and ecosystems doing so that we target conservation action on the elements of biodiversity that are rare, at risk, or declining. Using element occurrences and other data types, NatureServe conducts conservation status assessments for species and ecosystems occurring across North America. We assess the extinction risk of species and ecosystems at a global, national, and subnational level. And our network programs also assess the conservation status of individual element occurrences. Our work here also includes assessments of climate change, vulnerability, and ecological integrity, documentation of threats, and the development of biodiversity conservation metrics. Now we'll look at our conservation status ranks in more detail. Our ranks are assigned using a 1 to 5 scale, with 1 being critically imperiled and 5 being secure. Our status ranks consider rarity, threats, and trends. Our global conservation status ranks, or G ranks for short, represent the overall extinction rate of the species or ecosystem across its full range. National and subnational conservation status ranks are also assigned, representing the status within a more limited geography. So, for example, a species may be globally secure, but rare and of conservation importance for an individual state or province. NatureServe is an IUCN Red List collaborator, and our conservation status ranks are roughly comparable to Red List categories, as shown here in the image. We will describe our conservation status rank methodology in more detail in Part 2C of this training. So now that you have a better understanding of the data we develop and manage, let's talk about how you can access this information. There are 3 basic ways. First, a vast amount of NatureServe data and analytical products are available for free to the public under several online tools, including Explorer and Explorer Pro. Second, under a licensed subscription, you can access more precise species locations and native resolution species habitat models, along with other data products. And if you can't find what you need on our website, you can contact us directly. We have expertise in habitat modeling, biodiversity metrics, and other types of biodiversity analysis. For many years, the primary way of getting our data out has been NatureServe Explorer, our online biodiversity encyclopedia. It includes profiles of species and ecosystems, including information on conservation status, distribution, trends, and more. You can search NatureServe Explorer by taxonomic group, conservation status, or state, province, or territory. Our new sister tool, NatureServe Explorer Pro, has an online map viewer that allows users to explore more detailed species location information and generate site-specific biodiversity reports. Explore species distribution data in an online map viewer using NatureServe Explorer Pro. In addition, NatureServe has published predictive habitat data layers, international biodiversity indicator dashboards that visualize biodiversity data for several countries. We have other publicly available data and data products available on our open data hub. If using our publicly available data on NatureServe Explorer and Explorer Pro and our other tools mentioned, you can contact us about different paid subscriptions that provide access to more precise locations of species and natural communities and species habitat models. These data are provided under standard license agreement terms. Non-GIS users can filter, view, and interact with species location directly on the mapping interface. Users can draw or upload a boundary and run a biodiversity report for an area of interest. NatureServe Explorer offers a geodata portal. So in addition to the map viewer, GIS users can access the same data through the geodata portal so that data can be downloaded or utilized on local GIS systems. As mentioned, our network of biodiversity and GIS professionals and the unique and precise biodiversity data sets we maintain support our ability to analyze data to guide prioritization of species or areas on the landscape in need of conservation protection. We can assess the impacts of climate change and other threats and develop and ground truth species habitat models. We are also working with our U.S. network programs on the development of environmental review tools, and with other countries, as I mentioned, to develop and visualize biodiversity indicators. So custom analyses and tool development are skill sets we offer as needed. So in summary, we welcome you to explore our public data offerings on Explorer and Explorer Pro, or download the U.S. county and 8-digit HUC watershed data that are available through the Esri marketplace. You can also submit an online data request form, or just email us at datasupport@natureserve.org, and we're here to help. Welcome to Part 2A of NatureServe's data use training, Understanding Documented Distribution Data. In this part of the training, you will gain an understanding of our most well-developed and utilized spatial data product, the element occurrence data set. and other types of documented distribution data available through NatureServe. Here you see a map showing element occurrences, or referred to as EOs, of species that have been ranked either critically imperiled G1 or imperiled G2. The blue areas on the map are areas that have been visited, assessed, and documented over the last 50 plus years by our network of species biologists in collaboration with other conservation partners using standard EO mapping methods. EOs represent areas of high conservation value that contribute to the long-term persistence of the species or ecosystem that is mapped. EOs are standardized to have consistent taxonomy and consistent mapping methods across their range. The element occurrence is a unique concept that was developed by NatureServe and our network programs in the 1970s. Element occurrences have observations at their root, but not all observations are appropriate for the development of an EO. In this slide, you see this illustrated for the piping plover. A species biologist walking along a stretch of Virginia coastline documents 6 observations of the piping plover, but only 4 of these observations are suitable for the creation of an element occurrence, and I will explain why. The 4 nest sites outlined in green are areas on the landscape that can be mapped and are critical to the persistence of this species. The 2 sightings of piping plovers flying overhead, outlined in orange, can also be valuable for other types of assessments, but are not areas on the land and or water that contribute to the persistence of the species, which is the definition of an EO. So they would not be mapped as EOs. In addition, nest sites 1, 2, and 3 are in close proximity to each other, whereas nest site number 4 is more than a mile down the beach. Using the EO separation distance mapping rules for this species, nest sites 1, 2, and 3 would be mapped as one EO, whereas nest site number 4 would be mapped as a separate EO. These standard mapping rules ensure that biologists in other states where the piping plover occurs use the same rules when mapping these species. This contributes to standardized and comparable information that can inform not only conservation action on the ground, but also ensure consistent data to inform the range-wide assessment of these species. Now, to further illustrate the difference between an observation versus an element occurrence, I have a little quiz. Which of the following observations would be mapped as an EO? A bald eagle fledgling sitting on a light post in a parking lot. No, a parking lot is not an area on the land critical for the bald eagle's survival and therefore not an area of conservation value, so it would not be mapped as an EO. A rare sighting of a bird outside its normal range during a hurricane event? No, because this species is not found within the habitat it requires to persist and therefore would not be an area to target for conservation. A piping plover nest with eggs along the Maryland shoreline. You're going to get this one right. Yes, taking steps to protect these nesting areas will contribute to the survival of these piping plovers. A white-tailed deer in an open field within a protected area like a state park? No. The white-tailed deer would not be mapped as an EO because it is a common and secure species, and NatureServe and our network programs do not track and map the locations of common, secure species. We focus on mapping rare, at-risk species and declining species. And lastly, a rare orchid in its natural habitat. Yes, this is an area that is definitely important to protect. So next, we're going to look at one of the attributes of an EO. So when we map an EO, there's several attributes associated with the EO that help you to understand it, and I'll be talking about some of these attributes. One of the most important attributes is called the element occurrence rank, or EO rank. When creating an element occurrence, we use standard methods to evaluate the condition of each map location of a species or ecosystem. The EO rank is assigned based on the estimated viability or ecological integrity of the EO and considers things like existing stressors and restoration needs. The element occurrence rank, or EO rank, uses an A to D rating, with an A rank indicating that an EO is in excellent condition versus a D rank indicating that an EO is in poor condition, due to the factors I mentioned. There are other rank values listed on the lower portion of the slide. Some of these are assigned when there's insufficient data to actually assign an A, B, C, or D rank. The factors that are considered when assigning an EO rank are documented in the EO record. So this attribute helps you to understand when you look at an EO and you see that it is in poor condition versus excellent condition, you can make decisions about targeting restoration for poor condition or fair condition EOs, and also targeting protection activities for EOs that are in excellent or good condition, because we clearly want to keep those EOs in excellent or good condition. So now that you understand what an element occurrence is, let's see what they look like on the map. This slide includes an image of EOs as they would be displayed in NatureServe Explorer Pro. All the areas in yellow are element occurrences. In this image, I've clicked on an area, a polygon in the center of the screen, and you can see that it is lit up in a light blue color, indicated by the arrow here. The pop-up to the right displays the various attributes associated with this small EO that we have selected. First, we see that this polygon represents an element occurrence of the obscure Indian paintbrush. We have documented both the scientific and common name here. Next, you see that the element occurrence rank is ranked as a C, indicating that this EO is in fair condition and has a fair level of viability. In addition, we see that this EO was last observed in 1989, and that its accuracy has been documented as high, communicating that the mapped area accurately represents the actual observed area. And last, we see a couple of range-wide statuses for the species. So this species is considered a G2 or globally imperiled, which means that it's considered imperiled throughout its entire range. And then we have an S subnational rank, in this case, state rank of S2, which indicates that at the state level, it is also considered imperiled. Here is the same image, but this time I've clicked on a larger EO to the right of the small one that we just looked at. In this case, the polygon represents the Mount Rainier lousewort. It has an EO rank of A, indicating that it is in excellent condition, and that it was observed in 2007, and that it has a medium accuracy rating, which means that there is uncertainty as to whether the area observed captures the full extent of the species, or that the species occupies the full area mapped on the screen. In this slide, we're looking at a different area that has an EO shaped like a hexagon in the lower left side of the screen, also lit up in blue. A hexagon-shaped EO indicates that the EO has been generalized. NatureServe offers our network programs 4 hexagon grid sizes, 1, 7, 49, and 343 square mile grids. And these are used when the data locations need to be obscured. So when we look at the pop-up screen, we see also that the EO data generalization flag has been applied that indicates that this EO has been generalized. This is an EO for a leopard frog, and since many amphibians are prone to collection, this EO location has been slightly generalized to a 1 square mile hexagon area to protect the location from getting into the wrong hands or misinterpreted. So the last 3 slides I showed you are meant to illustrate the fact that many different factors can contribute to how an EO is mapped and displayed, and some of the attributes you need to consider when using EOs so that they are accurately informing the conservation decisions you're trying to make. In summary, an EO can encompass a large area because the species is naturally very wide-ranging, like the Florida black bear. In some cases, an EO may be slightly buffered because there is a level of uncertainty as to whether the area observed represents the area occupied by the species, like we saw on the last slide. And in some cases, the sensitivity of the species or the species location can cause it to be generalized by our network programs, as in the case with this leopard frog. We will talk a little bit more about why this data is sensitive in part 3 of this training. Hopefully, you now have a better understanding of the element occurrence and how they rely on but are different from observations.
Welcome to Module 2B of NatureServe's Data Use Training, Understanding Modeled Distribution Data. In this module, We will orient you to NatureServe Network species habitat model products, help you understand how to best apply these products, and point you to resources to learn more. At the end of this module, you should understand how our habitat models are produced and reviewed, how to interpret the model outputs, and our model confidence assessment framework. That is, how to find out information on how well a model performs and what that means for how it should be used. NatureServe defines habitat as the combination of resources and environmental conditions that promote occupancy, survival, and reproduction by individuals of a species within its range. Our habitat models map where on the landscape those environmental conditions exist. Put a little bit more simply, our mapped model outputs identify places where a species is more or less likely to occur. An example is shown at the right. Here, we've mapped areas of low, medium, and high probability habitat for Apalachicola false rosemary, an imperiled plant. We deliver these maps to our data users as part of our licensed data products. Public versions of the models will soon be made available as well. Alongside these habitat maps, NatureServe provides information on factors driving the prediction, how well the model performs, and how we recommend it be used. Because habitat models are predictions, some models perform better than others, and understanding model performance is important for understanding how the models should be applied. Don't worry though, we'll walk you through how to do that. Most NatureServe Network habitat model products are produced through an inductive modeling process. To train our habitat models, we start with NatureServe Network documented distribution data, sometimes supplemented with data from additional sources. Documented occurrence for species are intersected with environmental predictor layers, things characterizing the environmental factors to which species respond, like climate and soils and land cover and elevation. Using sophisticated machine learning techniques, we characterize the environment where the species is known to occur and map where else on the landscape similar conditions are found. Outputs include a probability surface indicating from low to high the likelihood that a pixel provides habitat for the species in question. The continuous probability surface is then categorized to depict areas of low, medium, and high probability habitat. At various points along the way, the model inputs and outputs are reviewed by species experts to ensure that the AI-generated results are a meaningful prediction. This process is highly iterative. Initial models are refined over time based on expert review or when new field data becomes available. The cycles of reviews and refinements improves the quality of the prediction over time. One of the real strengths of habitat models is that they can complement documented occurrence data. The map at left shows the county range map in green and documented occurrences for the frosted flatwood salamander in yellow. With this information alone, it's hard to know, are the places with documented occurrences places where the species doesn't occur, or just places where nobody's looked? Our habitat models fill in those gaps in understanding. Places shown in purple are those likely to support the species, as we've said, while places without color are places where the salamander would be pretty unlikely to thrive. Areas without predicted habitat represent a significant portion of the map species range shown in green. Range maps alone can really overestimate habitat. Documented occurrences, as we've said, can underestimate habitat. While there's uncertainty associated with these models, they provide that great complement to these other sources of distribution information. Let's talk for a moment about the different habitat categories shown on these maps. NatureServe models classify all pixels within the species range as either high probability habitat, medium probability habitat, low probability habitat, or non-habitat. High probability habitat is areas that are optimal for species occurrence. Environmental conditions at that location are nearly identical to conditions where the species is frequently observed. The probability that an individual of the species would be found in that location is high. On the other end of the spectrum, areas classified as non-habitat are those where environmental conditions are dissimilar to conditions where the species observations have occurred. The habitat is considered unsuitable. The species is not expected to be found in this location unless incidentally passing through. We bin the continuous model prediction into these categories using statistically defined thresholds, while also taking into account recommendations made by experts who know these species best. Users should consider their own specific management needs when deciding which habitat categories to use. For identifying areas of greatest conservation value, areas of high restoration potential, or areas where field surveys could help find new occurrences, the high probability category is probably most appropriate. In cases where a user wants to be more protective, for example, if considering whether to survey for an endangered species before land is developed, it may be appropriate to also look at those areas flagged as medium or even low probability. As mentioned previously, habitat models are just predictions, and some models do perform better than others. Model performance can depend on many factors. Some species are easier to model because they respond to very specific environmental factors that are easy to map. For example, it's relatively straightforward to produce an accurate model for a rare range-restricted plant that's found only at certain elevations or on certain well-mapped soil types. Conversely, it can be really difficult to arrive at a good model for, say, a wide-ranging bat that requires specific roosting habitat that's not well captured in existing environmental data sets. To help users understand how much they can trust a given model and what kinds of applications it's appropriate to be used for, NatureServe has developed a model confidence assessment framework. A model confidence score is assigned to each model based on 3 factors: the integrity of inputs and methods, statistical validation of outputs, which is performed as part of the modeling process, and expert review of the model outputs. Is the prediction consistent with what those who know the species well understand about its habitat? The confidence scores provide a measure for the uncertainty associated with the model. It's worth noting that in some cases, a model can be assigned a low confidence rating, even if it provides what's fundamentally a good prediction. A model may perform well, but if it has not been fully vetted by experts, we might not have confidence that the model performs well. In the example shown on the screen, a model was assigned a medium confidence score for the integrity of inputs and methods and a medium score for statistical validation. It scored low for expert review, either because an expert looked at the model and didn't like what they saw, or, as is more often the case, because the model has not yet received comprehensive review across its entire range. In this situation, the overall model confidence is rated low. For low confidence models, recommended uses include range determination, guiding field surveys, which can then be used to further refine the model, and things like conservation planning at pretty broad scales. If that model review takes place and experts agree that the model performs well, but perhaps isn't an exact match with their understanding of habitat, the expert review score moves to medium, and the overall model confidence rating also moves to medium. Recommended uses for this model now include conservation planning at finer scales, things like climate change vulnerability assessment, initial environmental screenings, and informing listing decisions. If all 3 performance factors are high, the overall model confidence rating is high, and the model is appropriate for higher stakes decisions, like contentious environmental reviews and guiding species translocations. This is a really high bar. NatureServe is constantly working to expand our model library and increase the performance of our models. One way we do this is by iterative improvements, using the reviews provided by our network of experts and collaborators to improve the models over time. Here, you're looking at iterative refinements of a model for Apalachicola false rosemary. At the bottom, you see an expert rating assigned to each model, alongside comments received on model performance. The 3rd iteration of the model received a 5-star review and a high confidence rating. In our efforts to make best available information accessible, sometimes we will share low or medium confidence models as part of our model library. The confidence rating and model review comments, when available, are always included alongside the model so users can understand how the data are best applied. If you're interested in a habitat model not currently included in our model library, or in a higher confidence version of a model for a particular species than what's currently available, we can work with you. Now let's take a look at models within the Explorer Pro interface. Here, we're viewing data as a licensed Explorer Pro user. I've run a search for the frosted flatwood salamander, and the model results are shown here in purple. Zooming in, you'll see the three categories of habitat: low, medium, and high probability that we previously discussed. Click on the information button next to the model, and you'll see the model confidence and recommended uses. To see the full metadata for the model, you click through to a link. The metadata for species habitat models gives details about model inputs and model performance. This includes an overview of the model confidence and recommended uses. It includes information on the data used to train the model and details on the thresholds used to define the model categories. The metadata provides information on which environmental predictors contributed most to the prediction. Continuing on, you'll find additional details on the confidence scoring, as well as graphs showing more specific information on the environmental predictors and the species response to those. If you'd like to learn more about our modeling process, the NatureServe Network Species Habitat Modeling Standard is a good place to start. It includes definitions shown on the previous slides, defines standard attributes, and provides details and reasoning behind the model confidence framework. It also provides a blueprint to support model sharing from multiple sources that we will continue to deploy as we add additional models to our library.
The Part 2C of NatureServe's data use training, Understanding Conservation Status Ranks. In this part of the training, you'll get a better understanding of our conservation status ranks and the methodology used to develop these ranks. Recall that the third fundamental question that NatureServe seeks to answer is, how is it doing? We answer this question in a variety of ways, but the most basic is through conservation status assessments of plants, animals, fungi, and ecosystems. Let's look closer at the NatureServe conservation status ranks. NatureServe and network scientists assign these ranks on a 1 to 5 scale, where 1 is for species and ecosystems that are critically imperiled with extinction, and 5 is for those that are demonstrably secure. For the global scale, which means the worldwide range of a species or ecosystem, these ranks are labeled G1 to G5. Other ranks include GH for species known only from historical observations and may now be extinct. Species ranked GXC are extinct in the wild, but persist in captivity, such as in a zoo, botanical garden, or seed bank. GX species are those that are extinct everywhere, such as the passenger pigeon or stellar sea cow. Some species are too poorly known to be assigned a rank. These are categorized GU. In the example on the screen, the piping plover has a rank of G3, meaning that the species range-wide is vulnerable to extinction. What information goes into a conservation status rank? Scientists used 8 factors grouped in 3 categories: rarity, threats, and trends. The rarity factors are geographical range extent, the area actually occupied by the species or ecosystem, population size for species, number of element occurrences, recall that you learned what these are in a previous section of this training, and the number of element occurrences with good viability. The single threat factor is threat impact, which integrates the scope, severity, and timing of the different anthropogenic threats affecting the species. And finally, short and long-term population trends also factor into the assessment. Although ranks are the most robust when information for all of these factors is available, ranks can still be calculated when values for only a subset of these factors are known. NatureServe status assessment methodology can be applied at 3 different geographical scales: the global or range-wide rank that we just saw, a national rank, or the status in a single nation, and a subnational rank representing the status of a single state, province, or territory. In our piping plover example, it is G3 globally and N3 in both the US and Canada. By looking at the map on the right, we see that subnational ranks vary across its range from SX in Indiana to S3 in Saskatchewan. NatureServe status ranks aren't the only ones used. You may be familiar with the IUCN Red List. The Red List uses categories to describe estimated extinction risk, which is derived from rules that consider population trends, range size, threats, and other factors. Although some prominent plant groups and most vertebrates have been assessed for the Red List, most North American plants have not been assessed. The same is true for most invertebrates, such as insect pollinators and freshwater mussels. IUCN's categories can be roughly crosswalked to NatureServe status ranks, as you can see here. And with that, we conclude this brief discussion of conservation status ranks.